this week, we have Chentian coming in to present a work she just recently submitted, and that was done while she was at interning at DeepMind. So Chentian is pursuing an informatics PhD at the University of Edinburgh, where she is supervised by Dr. Chris Lucas and Dr. Frank Molucca. Her research interests lie at the intersection of computational cognitive science, reinforcement learning, and causality. She recently completed an internship at DeepMind with Dr. Hado van Asselt, and will be presenting work from this internship. So we're very glad to have you here today, Chentian, and we're looking forward to a presentation. Thank you.
Okay, yeah, thanks, Sam. Yeah, I'm just excited to, I guess, present work that I did on my internship with Hado, who was my host, and also collaborated very closely with Rosemary. And it's about learning how to infer partial MDPs for in-context adaptation and exploration. And I am very happy to take any questions, discussion points in between, as well as after the presentation. And yeah, I'm not sure if I'll be able to see if people raise their hands. So can you let me know about that, Sam?
Sure. I'll keep an eye out.
Okay, thanks. Then yeah, the umbrella problem that I'm interested in, and so how I know Sam through like the RL generalization group here. So the problem that lots of us are interested in is how can an agent generalize across tasks? So like how can it acquire some sort of general knowledge about the structure of like transition functions or like reward functions that it's seen in previous tasks, and use that knowledge to help it act well in new tasks. And then the specific flavor of this kind of question that I'm interested in is like in that new task, how can that agent leverage the knowledge it acquired before in order to explore how the new task works, as well as adapt its policy to acquire high rewards in that task. And then how can it do so in context, in the sense that it doesn't use any gradient updates, but all it relies on is sort of forward passes through a neural network, and context, which is just the state, action, or reward that it's observed so far. And so I think a promising approach, or to first sketch out a promising approach to this sort of like in-context adaptation and exploration, taking a bit of like motivation, inspiration for some of the PhD work that I did before starting the internship, which is on sort of like Bayesian models of human behavior and human learning. So in this sort of framework, maybe like a nice way to start approaching the generalization problem is to say, let's say we've seen some past like training tasks before, and we're able to use what we gained from those tasks to form prior beliefs about a new task that we're in. And from those beliefs, we can sample some sort of hypothesis. Let's say, what are the dynamics like in the current task that govern, say, like how objects interact with each other here. Given this hypothesis, we can pick actions by acting as if the hypothesis was true. So for example, acting optimally under that hypothesis. Once we take an action, we can observe the next state given to us by the environment, append that to our history of actions and states, which is what I call context here. And then that context can then inform our beliefs, or like update our beliefs, both in the sense of like it tells us whether the hypothesis that we just tested was correct or not, and it helps us update our broader beliefs about how that task works. And why this is nice for like exploration adaptation is that in the beginning, we might have the sort of like more uniform beliefs. So then when we sample hypotheses, we would sample many different hypotheses that lead to quite varied actions. So that would help us explore around in the environment. But then once we observe more context, then we have more information to tell us, to sort of like converge our belief to something more certain and like closer to like the correct rules of the task. So then once we sample hypotheses, those hypotheses would be very good, and thus our actions would be very good and like adapt to help us in that task. And it turns out like this sort of framework is very neatly encapsulated by a computational framework called posterior sampling, also known as Thompson sampling, originally from the Bandit literature, and then extended into the RL setting. So for posterior sampling, I guess the details of how we maintain beliefs and like update beliefs is through Bayesian inference, and then our hypothesis space would be Markov decision processes, or MDPs, that potentially describe the current task that we're in. So then when we sample a hypothesis, we would sample one of these potential MDPs, and then acting under that MDP is through like dynamic programming on that MDP so that we can obtain the optimal policy for our hypothesized MDP. And then using that policy, we can pick one action or like in general, a few actions, and then observe the next state. And again, append that to our context, which is then inputted into the Bayesian inference machine again to help us update beliefs over MDPs. So this framework is really nice, but it's hard, like in its original form, it is impractical in the sense that Bayesian inference often involves unknown quantities, like what kind of prior is it reasonable to start with, or like maybe we don't have an exact analytical form for a posterior update, so how can we approximate that sort of posterior update? And dynamic programming for larger MDPs is very expensive. And so this is the motivation that leads into our proposal for a method, which is based on posterior sampling. But instead of doing exact Bayesian inference, we take a transformer and some training tasks in order to learn like an approximate inference process over MDPs, where that process includes both like the prior of what sort of prior distribution over MDPs is reasonable to start with, given what we saw in our training tasks. And it also includes the posterior update rule, given new context, what is the most reasonable way to update a distribution over MDPs. And in order to make the dynamic programming process cheaper and more practical, our hypothesis space, or like things we sample, are partial MDPs that don't describe like everything in the task, but just a small subset of that, such that they have very small state space and action space that is cheap for dynamic programming. And we represent these small MDPs as graphs. And an example of that is this little graph right here, where our vertices on the graph represent states. Traversing through the edges represents actions, and then the existence of edges, which sort of like the probability that an edge exists, or the probability that we can traverse across an edge, represents our transition function. Oh, sorry. And the reward function isn't shown here, but one way to represent that on the graph is to say like for each vertex or like state, or like for each vertex edge combination, or like state action combination, what is the probability that there is a positive reward there, for example. So in this small MDP shown here, what it describes is like this environment that we can imagine, where we have a wine glass on a table in our first state, and then it just says that if we push that wine glass, then it will break in the next state. So this is a partial model in the sense that it doesn't represent all the information that is needed to make that prediction about whether the glass will break or not. So it doesn't represent relevant things like where is the glass on the table or like how tall is the table. But nevertheless, we might expect that, wine glasses are generally quite rounded in shape. So once we push it, no matter where it is on the table, no matter how tall the table is, then it will likely just like fall down, roll across the table and break. So perhaps this sort of compact representation already contains enough information for us to find like not the optimal policy, but like a decent policy that is able to avoid the action of pushing the wine glass, for example. And it has the benefit of just being cheap to do computations over. So to return to the sketch of like posterior sampling that we had before and like sort of substitute in what the things that we just talked about is that we can take that belief part from the previous sketch and replace that with the transformer beliefs about partial MDPs, such that when we sample one of these partial MDPs, which is one of those small graphs like we just saw. And then we can perform dynamic programming on there and like continue the process that we saw before. And one additional thing here is that the transformer would also need to make this prediction or mapping from the current, or let's say the current action and state that it observes, or more specifically, the current state it observes. It needs to predict or map this state onto a vertex in graph space, so that we can use that vertex as a starting state to query the policy that we get out of dynamic programming, which would be on graph space or like partial MDP space. And then finally, there's the not shown invisible mapping from like, and like an assumed known mapping from the actions or like edge traversals in graph space back to actions in real environment space. And in order to investigate like how important is sampling in this entire procedure, we also analyze this ablation where we remove the sampling part and instead take the expectation of the distribution that comes out of the transformer. And yeah, in terms of like how the transformer is trained in its specific architecture, I am not planning on going into detail about that in this presentation, but I can mention like some key points about that, which is one that this particular transformer architecture is able to take in like an entire data set in supervised learning language, or like an entire context in our case, instead of a single data point or instead of a single action state here, which allows it to sort of make these predictions based on the entire history of what it has seen before, rather than just like what it is currently seeing. And the second thing is that it's trained to autoregressively predict these partial MDPs for which we have supervision signals. And it is trained on several different contexts matched to several different partial MDPs. So that allows it to be able to learn like for some context, there's like this distribution of possible partial MDPs and like what is the most likely one. Okay. And for the, or actually I can stop a little bit here and see if there are any questions so far.
Yeah, I had just one just to make sure I understood correctly.
Yeah.
So the transformer is learning this among other things, but it's learning this transformation from the original state space, the partial MDP state space.
Yeah.
And but you assume that you have a mapping from the partial MDP action space to the action space of the original MDP, right?
Yes, that's right.
Okay. Okay, then that's that was just wanted to make sure I followed through.
Okay, cool. Yeah, that's right. It's like the thing that we did here, which I didn't describe before, is we mostly compress the state space. So that's why we need to learn this many to one mapping, into partial MDP state space. And then the action space, especially in the environment that we consider, is quite small. And it's also like a different problem, or like a hard problem in that environment as well, to learn like how to map these like edge traversals on our graph into actions there. So that's why we've just fixed that, or like taken that as a given thing for now.
Hey, hi, Chentian. I already have a question too.
Yeah.
Thanks for presenting, by the way.
Thanks for having me here.
I want to ask, so it seems like the core contribution from what I can tell here is, besides predicting the MDPs, is that you are now saying because of the transformer, you can actually make this type of inference over the full history of the state actions you produced.
Yeah.
So I'm just wondering, if that is the main contribution here, wouldn't there be easier ways to test that out than going with a full-blown big transformer type of architecture? So, for example, what about just using a simple LSTM type of model in the first place?
I see. Okay. So I'm thinking of two things. In terms of the contribution, I would say that's like two parts. One way is to do this approximate inference process. And the second thing is to sort of test out, like, can we use these partial representations within posterior sampling and still get decent policy adaptation, even though dynamic programming and like posterior sampling usually assumes it has access to like complete MDPs. And so for the first part on like learning the inference process, so perhaps it might not be that important, like which exact method is used to learn approximate inference in this case. Our choice of this transformer architecture that we have is because it is based on previous work from Rosemary, which has already been shown to be able to learn inference over graphs. So that's sort of like the main motivation for choosing a transformer in this case, but I have not tested out like other methods for learning inference. Does that answer what you were thinking of?
Yeah, so I guess it kind of answers, but it doesn't seem like a very good answer.
Oh, okay, I see.
I mean, usually you want to eliminate any confounding factors on the periphery to explain any performance gains. And it seems here you have a gigantic pool of all kinds of potential confounding factors that can explain performance benefits, because there's a lot of stuff happening in transformers. I'm just thinking,
I see.
If you want to establish just the ability to learn a useful partial graph embedding with the sequence as the input, I would probably, first of all, choose the simplest type of approach that allows me to test that out. And then only if there's some serious bottlenecks, you can go to these more complicated models. So I'm wondering whether you should perhaps include a simpler type of baseline that just uses the off-the-shelf LSTM. And then maybe if there's some important performance loss, you can try to explain where it is to perhaps a bit more strongly justify why you really need transformers in this case.
I see. Okay. Yeah, I think that makes sense. And in practice, unfortunately, it would be hard for me to test that because I no longer have access to the code. But yeah, that makes sense. I would take it with me as like feedback to like think about. And
it's one of the annoying things about these internships, right?
Yeah.
I had one more question.
Yeah. Oh, so, sorry. Before your next question, so I was thinking about one thing, like what you were saying about the transformer and like why a transformer might work well here. So another thing that we haven't like you said, eliminated the confounders for, but is a hypothesis for why it works well here is like that ability to do attention. In this case, we do attention over the time step dimension, which allows us to see like what is the relationship between all of these observations that we've seen before, which can help us make this sort of like inference that depends on all of them.
Yeah, that's exactly the next thing I wanted to ask.
Okay.
So that's interesting, but I'm seeing there could be some strange pitfalls here.
Okay.
Because if you use a a textbook style Bayesian inference approach, then you know that as long as the correct hypothesis is in your world space,
yes,
that you will, and if there's sufficient differentiators between the hypotheses, that you will converge in your posteriors to that. And that's nice about Bayesian approach. But if you now have some sort of attention mechanism and you give it flexibility to reweight the evidence, basically, I'm thinking you can also, you might give it arbitrary, almost sort of flexibility to deviate from a correct posterior inference process. And it gives you some type of inference, which is not actually inference. It's just, you see what I'm trying to say? Posterior inference is well defined, but this could actually come up with any sort of thing. And I'm wondering, what are you doing to gain some confidence that this is actually a correct approximation to any sort of type of posterior you would ordinarily obtain?
I see. Okay. So kind of a related thing first, what you're saying, like having Bayesian inference. So like if we did vanilla Bayesian inference here, and that would need us to specify the entire hypothesis space up front, which would include like what could happen in our training task as well as what could happen in our testing task. So in that way, it would already need knowledge about the testing task. Whereas with a transformer approach, maybe we don't have that guarantee that will definitely converge onto something that we know is in our hypothesis space, but we can train it on, or like what we've done is train it on some training tasks and then like held out the hypotheses that are that describe the testing task. And then we see that because the transformer doesn't need to have the hypothesis space up front, it can actually still generalize to the hypotheses in the testing task. But in terms of like guarantees, like you were talking about, so the way that we've set up our loss, I think may be able to address that. So the way that I've set up the loss is like an expectation over sort of the joint distribution of contexts and partial MDPs, such that if we minimize the or if we get the maximum likelihood estimation for our transformer parameters under that, then I think that should like be equivalent to minimizing the KL divergence between at least what we see in our data and the transformers outputs. So in that sense, maybe we get some guarantees for like being able to make good predictions for our training set, but not directly for making good predictions in our testing set. And we only really have like empirical performance on the testing set for now.
Yeah, that was going to be my suggestion. So I see, I understand what you're saying, but I think there might still possibly be some benefit in exploring a regularizer in your loss terms when you want to regularize the inference, at least in the within training distribution, as you suggested, I think, right? And in a way, it's almost like you're forcing your model to be disciplined about doing a proper inference process and not some sort of arbitrary guesswork that just helps to maximize performance. But you want to have something that approximates the posterior in some sense appropriately. And I'm wondering if you incentivize this during training, maybe this actually has an interesting effect on how it generalizes, because it's almost like you're really asking the model then to make sense of the evidence in a particular way that actually functions like a likelihood function in the posterior production. And that maybe that alone helps you with the generalization. Because now if I'm imagining you have an intention mechanism and it arbitrarily picks out pieces in the sequence which it thinks helps, but they're not actually what a proper posterior would do, then this could actually also almost like really badly fall apart when you then generalize to outer distribution spaces that have very different behaviors, because these pieces that I'm paying attention to might not matter anymore in some way, whereas a classic posterior sequence would sort of wash that out, right? It would understand the unless the new outer distribution set is really badly mismatched from the within distribution, then you also get problems there. But I'm just wondering if that's a different type of baseline that you can also investigate, add some other type of value in your work.
So to make sure I understand, like another type of baseline that is incentivized to, in some way, like more directly to make sure it's like aligned with posterior inference, like let's say exact posterior inferences.
Yeah, something like that. If you have because in the within training distribution setting, maybe there's a way for you to calculate or with a Monte Carlo approach approximate a nearly exact posterior, and that can maybe be a part of your loss term that you can then use to regularize the training. And I have no idea what will happen, but it's just sort of a blue skies idea that could be useful to investigate.
Yeah, that makes sense. And yeah, again, in practice, I might not be able to test it, but we've also, like in other presentations, people have also discussed this. Like it would be interesting to see, since like on the task that we do, actually like we compare to exact Bayesian inference, so it's small enough to do exact Bayesian inference on. So during training, what we do right now is like we make autoregressive predictions of like one partial MDP or like one graph for an entire context at every time step in that context. But a way to make it closer to posterior inference, like you say, is like have a Bayesian model run alongside it and see what the current Bayesian model prediction is, and then just set our loss to be trying to reproduce the Bayesian model's prediction instead of just trying to reproduce the ground truth, which we may or may not have enough evidence for at this point.
Okay, cool. And then just one last thing. I'm sorry for taking up so much time. I feel like things to say.
Thank you for feedback.
The last thing is, so we have some collaborators at Technion in Israel, where we're also looking at context-based MDPs and POMDPs for generalization style problems in RL. And they're actually also using a graph-based approach, but not what you're doing. There we're using reward machines, which is a graph-based abstraction of the reward function. And I'm wondering, so just some of the keywords seem to be matching with what you're presenting here, and maybe there's an interesting conversation to be had here. So if you're interested, I could perhaps connect you with some of the collaborators there, and then you can share your paper. And I'm also already asking Sam to if you can share the recording from this talk with some of the guys there, if that's okay with you. And then maybe we can talk together and see if there's some opportunities to do something nice.
Yeah, I would be really interested in that. And like generally, I guess going a little bit more like neurosymbolic, taking graph representations of MDPs instead of like representing, let's say, the transition function within the weights of a neural network, like that sort of general approach I'm interested in, and just like learning more about and see what they're doing as well.
All right, cool. Yeah, we can do then in the coming days then, okay?
Yeah, thanks.
All right, back to you then. Sorry for taking so much time.
Oh, that's all right. Okay. I'm just gonna check on time. Okay, we have 30 minutes left. And yeah, I think I should be able to get through this. I might skip a few things so we have some time at the end for questions as well. So, okay, so after methods, onto the benchmark that we choose. So we want this benchmark to have like two properties. First is a supervision signal for partial models, or like these graphs that we were just talking about, because here in this work, we wanted to focus on not on learning how to represent like tasks as partial models, but instead of like given good representations that we can use as a supervision signal, how can we learn a distribution over those models? And then we also want the benchmark to be good for evaluating exploration and adaptation in new tasks. And that's why we look at the Symbolic Alchemy benchmark. And first, I'll show you like this 3D visualization just to explain what's going on. But we use a symbolic version of this. So in alchemy, you sort of have some stones, like this sphere here, or like this pyramid there, and you have some potions. And by dipping stones into potions, you can transform the stone's shape, color, or size. And then there's sort of like this, like different configuration of features have different associated rewards. And there's one configuration of features that has the highest plus 15 reward. And you can, so you want to like transform your stone into that configuration. by dipping it into potions. And in order to get the associated reward, you need to deposit your stone into the cauldron. And yeah, again, what's nice about alchemy is that based on this general framework of how a task works, we can generate like particular tasks with different transition functions or like different underlying partial models that we can use as a ground truth for training our transformer. And so let's take a look at how like each of these partial models sort of define one of these tasks. If we look at the one here in this corner, we might start with a purple, small, and sharp stone. And then if we dip it into the blue potion by traversing this edge, we can transform it into this rounder shape. And then using the yellow potion, we make it bigger. And then using the pink potion here, we make it sharper in order to get to this plus 15 stone, which we would want to then put into the cauldron. So again, here we have the states as like, or like the partial states are vertices, which actually just represent stones here. And then edge traversals are actions, which correspond to the potions here. And the transition function is like whether or not an edge exists. So whether or not given some stone potion combination, we're going to be able to transform our stone into some target configuration of features. And these partial models are partial in the sense that they don't encode information like whether potions are empty. So this graph always basically assumes that potions are full. So if we instead have an empty potion, like an empty blue potion, and we try to use it, we might get stuck if we just try to do planning or dynamic programming on this partial model. But again, we think that this partial model captures like the essential transition information within the task. And so we expect that using this within posterior sampling and with dynamic programming should be able to get us good policies. And so alchemy also evaluates exploration, adaptation in the sense that like within an episode, the MDP or like transition function is the same, but across episodes that changes. Or in other words, the cube changes or like the existence or absence of edges in the cube changes. So an agent needs to be able to explore those new transitions in a new episode, as well as adapt its policy in order to make use of that knowledge to transition toward the highest reward stone. And then within an episode, there are also some other things that are happening, like episode is split into trials, each of 10 time steps in our work. And so within or across trials, what you get is like the stone's initial features are resampled and all of your potions become full again. So it's more like perceptual things that change across trials, and then like the task itself or like the transition function that changes across episodes. And yeah, so actually alchemy is a playground for like a large array of problems that we can explore, but we are especially interested in sort of like generalization across tasks with different transition functions. So that's why we simplified alchemy down to this problem. So we only have one stone. Again, that's randomly resampled per trial. We have 6 potions, 1 for each possible effect. And there are 10 time steps per trial, and what changes across episodes is just those cubes, edges, or like the partial transition function. Okay, so now sort of returning to the sketch that we saw before, in order to adapt this for alchemy, what happens is that the output that comes out of our transformer is not an arbitrary graph. We actually constrain it to be this particular graph that's called a cube here, because it has 12 edges that may or may not exist and only like 8 possible states on each of those vertices. And then when sampling one of these cubes, oh wait, first I should say like the colors here indicate like the probability of each edge existing or not. And then by setting those probabilities as like Bernoulli distribution parameters, we can get a distribution out of our transformer, and then we can sample from that Bernoulli distribution to get 1, 0, like absent or like present edge values here. And again, we pass that through dynamic programming, append the results to our context. And for our results, so how well do we explore and adapt a new task with this method? And we consider a set of like 10 held out cubes, which were never seen during training. So the transformer has never seen this combination of edges before. And for each cube, we generate 20 episodes and evaluate how like adaptation and exploration within a single episode, and then like average over all of those for our metrics. Okay, so let's first look at how well does our method adapt its beliefs about the partial model with respect to the ground truth partial model. So the things that will be compared here include our method, which approximates those things in posterior sampling, as well as our ablation, which removes the sampling component in favor of taking the expectation. We also compare to some naive baselines called non-adaptive posterior sampling here, and that just represents like if we never update our distribution over partial models and we just always have a uniform distribution of a partial model, so that we randomly sample models. And random policy just discards models completely and just chooses actions at random. And then we compare against this set of oracles, including a true partial model. What if our beliefs had already converged on like a perfect partial model? Then what is like the upper bound on adaptation? And an exact posterior sampling is when we do exact Bayesian inference with a known hypothesis space of 109 alchemy cubes, which include like the cubes in the testing set. Then like what is like how fast does this exact posterior sampling method adapt its model beliefs? So first against baselines versus a non-adaptive posterior sampling, it stays here while our method and ablation goes down pretty nicely. So this y-axis here is partial model error, which is measured as like mean absolute error between the transformers or like just the predicted edges versus the ground truth edges in the cube. And now what's interesting is against the oracles, of course, the true partial model is going to be a flat line at 0 error here. Whereas the exact posterior sampling implementation with exact Bayesian inference goes down really fast and sort of gives us an upper bound on adaptation speed. So it's really nice to see that our method almost matches that speed and accuracy as well. And what we see here is that our method is a bit better than the ablation in terms of model error, which is interesting given that they are using the same transformer, which should be able to use the same or make the same like inferences. So what is happening there, we think can be explained by exploration. And so first but before going to that, let's first look at the same baselines again. And our y-axis is sort of like a measure of how much is explored with respect to the state actions in partial model space. So like up till now, how many unique vertex edges have we observed? So that's sort of like, it's supposed to be a proxy measure of like how much data have we gathered that might be useful for helping us distinguish between different partial models. And we see that these naive baselines explore quite a lot because they either sample models or actions randomly, whereas our method in ablation explores less, and here over-exploring, under-exploring are taken with respect to how much exploration is done by exact posterior sampling, which we set as a like ideal exploration, exploitation balance. within like the posterior sampling framework. And we see that our full method nicely, again, like falls almost on top of that exact posterior sampling oracle, and is also above this true partial model oracle line, which makes sense because true partial model already has the model, has no need to gain more information. All it needs to do is exploit that perfect information it already knows. So it is not, it has no need to explore. And so sort of like tying this back to what we saw before could explain why our full method is adapting its model beliefs better than the ablation. But it turns out like having sampling helps it explore a little bit more than the ablation, which means that it's probably collecting, or it is collecting more diverse information to be inserted into the context of the same transformer, thereby helping the same transformer sort of like see more and like be able to make better inferences about what the partial model is. And yeah, the last result is on policy adaptation. So all this time we've been using posterior sampling and thereby like dynamic programming on partial models. And it's not obvious whether that will lead to decent policies because usually posterior sampling, dynamic programming assume that they have access to complete MDP representations of the task. So let's see how well our method can do here. And here the y-axis is percentage of optimal reward, which is where optimal reward is sort of like calculated as if we had the complete and true MDP, what is the highest amount of reward that we can get in a testing task, and everything is normalized with respect to that. So again, our naive baselines aren't doing so well, but actually our method is like increasing its reward very well. And when compared to oracles, again, our method and ablation are quite close to that exact posterior sampling oracle in terms of like how fast we can expect to adapt the policy and like how much reward it gets in this case. And what's nice is that we see even with these partial model representations, if we have good representations, which is what the alchemy environment gives us, then it turns out like even just learning these smaller compact representations with much fewer states, and then doing dynamic programming on those can get us like very good rewards. And yeah, the last thing here you might notice is just the ablation gets a little bit higher reward than our full method, especially in the beginning, but then they become, right, here's clear, they become much closer towards the end. So what might be happening here is that our ablation, since that uses the expectation or like all of the information coming out of the transformer, it uses that to sort of construct a stochastic transition function using the probability values on the edges. And so when we perform value iteration on that, then value iteration or dynamic programming is going to consistently traverse edges that are likely to exist or that have high probability and are on the path towards the highest reward stone. And then in contrast to that, our full method, since it samples, so like even in, let's say in the case that our transformer has like high or like certain beliefs about that an edge probably doesn't exist when an edge does exist, but those aren't like exactly 0 or 1 values. Therefore, even for high probability edges, our method might end up sampling or like not sampling that edge. And then for low probability edges, our method could end up sampling that edge anyway. So it's like for the same transformer beliefs, our full method is sampling like noisier partial models, which then leads to like noisier policies that come out of dynamic programming. And that could explain why it is not consistently sort of like taking the most rewarding actions given like all of the beliefs that the transformer has right now. But actually, I think that is also why like that sampling procedure is likely to also help exploration and thereby model adaptation that we saw before. So I'd say like our full method is like desirable in the sense that it gets us all three of these things: model adaptation, exploration, and policy adaptation, albeit towards the end, while our ablation may be getting higher rewards in the beginning, but not doing so well in model adaptation and exploration. Okay, and then to conclude, the problem that we're interested in is how can an agent generalize in context to new tasks? And our proposal was to take the posterior sampling framework and say, how can we, or like, let's approximate the inference process using a transformer and training tasks, and let's use partial models to get us cheaper dynamic programming. And we saw that our method approaches the adaptation speed and exploration-exploitation balance of an exact posterior sampling oracle. But there is much future work that can be done, especially in seeing how we can sort of forego that supervision signal that we've relied on in this work. So how can we still learn useful partial models that are good representations of tasks in an unsupervised or self-supervised way? And how can we keep on learning like these very small models, even when we scale up to larger and harder generalization problems, for example, like the full 3D alchemy? And yeah, for the paper, I think Sam has linked it in the email, and here is a QR code as well if you're interested. And thank you so much for listening.